Kinetics. Let's talk about this new topic. This is the first time you encounter kinetics. And we're going to start first by talking about the activation energy, which after all is the key player in determining whether a reaction takes place fast or slowly. Alright, so let's talk about it. In the past, you may have actually seen, discussed, and maybe observed this type of diagrams. These are called reaction coordinate diagrams, where on the left side of the diagram you have the reactants and on the right side you have the products. What you have on the y-axis is an energy scale, and technically speaking what you're seeing here is how much or how energetic the reactants are in respect to the products. And for this particular example, the combustion of acetylene, we see that the reactants are higher in energy than the products. But the one thing that you may have not really analyzed all that much is this hump that the reactants have to get through before you even form any products. It's this hump that determines how fast or slow a reaction takes place. And specifically, if you measure the distance, or rather the energy difference from the reactants up until the very top of this hill, this is what we call the activation energy, and we abbreviate it as EA. But the activation energy is the energy required to pretty much get the reaction going forward. And the part that you may be familiar with is simply the energy difference between the products and the reactants. Subtract the energy of the products with the energy of the reactants, and that gives you the enthalpy of that reaction, which is thermodynamics. And that basically tells you whether the process can occur on its own. But it never actually tells you whether the reaction is going to happen in a fast or slow manner. That's what kinetics is all about, and that's what the activation energy is going to tell us. So this is going to be the topic of the center theme of kinetics. But as you are about to find out, there's a lot of steps that need to be taken in terms of data collection just to extrapolate the value of the activation energy. So we're going to go through each one of those hoops just to get to the final value, the value of interest. All right, now a few things that I'll also mention in regards to activation energy. Generally speaking, for reactions, when you start heating them up, so if you increase the temperature, you tend to increase the rate at which the reactions proceed forward. Okay, so there's an increase in that particular rate forward, and right here I'm giving you a constant K, which I'm going to be referring to in a little bit, but I'll just tell you right now, this is known as the rate constant, which increases with temperature, generally speaking. Okay, so the rate constant, as you're going to find out, is really a measure of how fast a reaction actually occurs. The higher the value of the K constant, the faster the reaction is in terms of how long it takes to go from reactants to products. And another feature that also needs to be mentioned, which we're going to touch upon later on, is the fact that at the beginning of the reaction, when you only have reactants, the only possibility is for the reactants to be turned into products. And as you increase the temperature, you increase the energy, the kinetic energy associated with letting the reactants go over the energy hill down to the products. Now, as time goes by though, you start producing more products and more products at the expense of reactants. So at one point, you're going to have a decent amount of products and a fair amount of reactants. And here the probability now becomes that the products could actually start reacting back. And for the products, the process of going in the reverse pathway from products to reactants is also aided by increasing temperature. So you actually kind of have a build-up or a specific setup in which you are going to get a certain amount of products and a certain amount of reactant. Now, how fast you get to that point is determined by the temperature. but you in essence get to a state that we call equilibrium, in which you have a specific number of products and a specific number of reactants. And that's going to be a topic we will be talking about on the next lecture. This is just kind of like a preview of that, being something that happens. But technically speaking, something that's kind of interesting to point out is that for reactions that happen to be exothermic, where the products are lowering energy, if you do increase the temperature, if you keep increasing the temperature, make it hotter and hotter and hotter, and the reaction is not to be exothermic, at one point you're going to make it very likely that the products are going to have enough energy that they're going to surmount the activation energy and go back to the reactants. And yes, the reactants have enough energy to go back to the products, but the fact is that now everything has enough energy to go over the activation energy hill. And so, technically speaking, raising the temperature for exothermic reactions at one point becomes detrimental in order to produce more products. So you actually kind of want to keep the temperature low if your reaction is known to be exothermic, right? And this is simply a result of the fact that both of the rate constants, the one going forward and the one for the process going backwards, are going to increase. All right. Now, another thing to point out too is that if you look at the correlation right here, the process forward has the regular activation energy associated with it. The process going back, technically speaking, is a measure of the products, the energy of the products going all the way up to the top of the hill. And that's known as the reverse activation energy, which if you look carefully, you realize just by looking at the arrows that the reverse activation energy is nothing more than the regular forward activation energy minus the enthalpy of the reaction. And that's what I'm showing you here in this equation. Now for endothermic reactions, the ones where you have a product of higher energy, you still have the same effect with temperature. If you increase the temperature, you increase the rate constant, but this happens for both products and reactants. And so now here, what takes place is that, yes, if you keep the temperature low, what ends up happening is that you may not have enough energy to surmount the activation energy going forward, but you may still have enough energy to surmount the activation energy going backwards because the products are higher in energy. So here, even though it's ultimately kind of detrimental in both circumstances, it's best to actually raise the temperature as much as possible because you want to ensure that you have enough energy to make it up to the top of the hill from the reactant side, even though the products will also be going to the back. But this is just basically something that you have to just deal with. You just can't get around that problem. So it's kind of a compromise of sorts. But in essence, having an endothermic reaction in general, you end up producing more product or aiding the product formation simply by raising the temperature, which is the opposite of exothermic reactions. And we're going to revisit this idea when we start talking about equilibrium. Once again, the reverse activation energy is given by the forward activation energy, which is presented here in pink, minus the enthalpy value, which, as you can see, if you subtract those two vectors, you're going to end up with only the reverse activation energy vector. Alright, so that's what I want to tell you in regards to the activation energy, what it represents ultimately, and how it tells us, pretty much the higher it is in terms of energy, the slower the reaction is going to be. The smaller the activation energy barrier is, the faster the reaction is going to be, simply because you're going to have enough energy to surmount that hill. But the higher the activation energy is, you might not have enough energy and you might have to heat up the reaction to higher temperatures. Alright, so we'll continue this discussion in the next video.